All right, we've already learned how to solve systems of equations by graphing. Now we're going to learn a technique called substitution. Substitution involves replacing a variable with an expression which is equivalent to that variable. This method is good or easy to use when x or y is isolated in at least one of the equations in the system. So when x or y is isolated. Notice in this little example I put down below here that y is isolated. So when they have a variable isolated with an equals between them, they're telling us that y is the same as 3x plus 1. Well, if y is the same as 3x plus 1, then the y and the 3x plus 1 can be interchanged. They can be used interchangeably. So what's going to happen is you're going to take the expression and plug it in for y in the other equation. Let's do some examples. This is an example of a consistent independent system. Of course, you won't know that when you start a problem, but a consistent independent is when you have the two lines crossing and you get one solution or one point of intersection. So notice that the first equation, y is isolated. So we know that y is the same as 3x plus 5. So what we're going to do is we're going to take the second equation. We're going to remove the y. We're going to keep the x and the plus and then the equals 1. But instead of the y, we're going to put the 3x plus 5. Because remember, equals means the same. So 3x plus 5 and y are the same thing. Now we can drop the parentheses and we have x plus 3x plus 5 equals 1. We can combine like terms. X plus 3x is 4x plus 5 equals 1. Now we're going to draw a line at the equals. We're going to move the 5 by subtracting. And then we have 4x on the left equals, this is 0. 1 minus 5 is negative 4. And then we divide both sides by 4 to get x by itself. And we get x equals negative 1. So we found that the x coordinate of the solution is negative 1. Now to find the y coordinate, we have to do another substitution. So I'm going to take the y equals negative 1, and I'm going to plug it into the first equation in place of x. So notice, I take the 3x plus 5, but instead of the x, I plug in the negative 1 that I just found. 3 times negative 1 is negative 3, and negative 3 plus 5 is 2, and that is the y coordinate of the solution of the consistent independent system. We're going to do another consistent independent system. Notice this time that we know that x is equal to 2y minus 2. So that means x and 2y minus 2 are interchangeable. So I'm going to take the x out of the first equation. Notice how I recopy everything in the first equation except for the x. So I put these parentheses. It's kind of like a bucket or a container. And into that container, I'm going to drop my 2y minus 2, my expression for x. Now I distribute the 3 to remove the parentheses. 3 times 2y is 6y. 3 times negative 2 is negative 6. Recopy the minus 2y, recopy the equals, and the 2. Now I'm going to combine my like terms. 6y minus 2y is 4y. Recopy the minus 6 and the equals and the 2. Now I'm going to isolate y by adding 6 to both sides. This makes a 0. Now I have 4y on the left equals 8 on the right, and then I divide both sides by 4, and I isolate my y value, and I get y equals 8 divided by 4 is 2. And that is the y coordinate of my answer. To find x, I have to do another substitution. So I'm going to take my second equation, x equal 2 times y minus 2, but instead of the y, I'm going to put this 2 right there. So y is 2, and then I have 2 times 2, which is 4, minus 2, which is 2. So my x coordinate of my solution is also 2. So the ordered pair 2, 2 is the point of intersection of those two lines. We also had one of our special cases, a dependent system where you have the same line twice and there are infinitely many solutions. So let's see what happens in the process of substitution. We know that y is equal to negative 2x plus 2. So I'm going to take the first equation, but I'm going to take out the y, but I'm leaving everything else the same. Now, y is the same as negative 2x plus 2, so I'm going to make that substitution. The parentheses can be dropped. A lot of 2's in this problem. And now I'm going to combine like terms. 2x minus 2x is 0. So now what am I left with? 2 equals 2. Well, duh, 2 equals 2. So if you get a true statement, a blatantly true, like 2 is 2, hello, then you know that it's a dependent system and the solution is infinitely many solutions. So the answer to the question is infinitely many solutions. Okay. Our other special case is the case of an inconsistent system where the two lines are actually parallel and they never intersect, so there's no solution. So that's what we're expecting here. Notice they're telling me that x is equal to 2y plus 5. So I'm going to recopy the second equation, but I'm going to take out the x and put parentheses where it was. I've got a minus 6y and I've got an equals 4. Now I'm going to take the expression for x, 2y plus 5. I'm going to plug it in where the x used to be, and then I'm going to do the math. 3 times 2y is 6y. 3 times 5 is positive 15. Recopy the minus 6y, the equals, and the 4. Now combining like terms on the left, 6y minus 6y is 0. So these cross out. And what are we left with? We're left with 15 equals 4. Huh? 15 equals 4. When is that true? 15 is never equal to 4. So this is like a false all the time statement. It's false. And when you see that, you know that you have an inconsistent system and there is no solution. Okay, so that's the process of solving by substitution. You have to make a variable expression substitution, and then you have to plug the number back in and make a second substitution. Thank you for watching.